Welcome back to System Software. So we're working on our compiler. Remember that our compiler project, the first compiler project, is up. And there is this handbook that walks through how each of the constructs in our IR language, all of the statements in our IR language, like assignment and function calls, can be implemented, a guide to implementing these. And the project description is here with the usual how to submit it with Git. The types of test cases and all that. So any questions on, and today we're going to continue on how functions are implemented. I'm actually going to show you assembly code and how the functions actually get implemented in assembly. Yeah?
Does the handbook cover kind of the C++ specific thing?
It does, yeah. So it handles, I think, everything you'll need for the C++ stuff. So the second section covers, I think, everything you'll need in order to, So I went through my completed version of the project and I picked out all of the non-C stuff. So this is basically how you do printf in C++. This is how you use, so this part, has anyone ever seen the arrow symbol in C? Hopefully you saw that. You should have seen this in CS1, right, for linked lists. I think you'll use that for linked lists. So it's the same in C++. You can think of objects as structs that also have function pointers in them. But if you just think of them as structs, then this is the same idea. So this is how you access parts of the tree. The tree is a tree data structure. So this is how you access parts of the parse tree. I've given you some code for accessing parts of the parse tree as well. And probably the last C++-like thing, which still looks a lot like C, is how do you iterate over lists of things in the parse tree. So whenever you have a star in the grammar, something like this is the list of parameters. So name plus means one or more names, one or more identifier tokens. This is how you can loop over those tokens. So it looks a lot like C, except these are vectors in C++ instead of arrays, and they come with their size built in. So you have the size in the actual vector data structure. Just think of it as an array where you can ask the array what its size is. In C, you don't have that in C arrays. So I think that's everything you'll need from C++ for writing this compiler. So that's really all the ANTLR stuff. The rest of it is just going to be C. Most of it is just really going to be doing some minimal amount of processing, pulling pieces out of the parse tree. It's going to be like pulling parts out of the parse tree and just printing out assembly code. So there's not going to be a whole lot of logic. It's just going to be kind of putting things in the right place in the assembly output. Yeah?
So you know how C++ repurposes auto for like something else?
Oh, yeah, that's true. I didn't even think of that. You're right. So, so this is not that's right. I wonder how their grammar works. But this is the type name auto, which is an auto, yeah.
You can also use it for what it does in C.
Like say auto. Say auto formals, maybe. Actually, I didn't even think of that, yeah. Probably, I feel like you should, because auto is a type name and it's also, I don't know. I'm not sure. It depends on what the grammar is. But yeah, try it. Let me know. See if you can do auto. Because this, as we talked about last time with function local variables, this will end up being a function local variable. So see if you can do auto. And it's automatically allocated by default, as we talked about last time. This is a C++ thing. It's called type inference, where you know how in C you always have to name or give the type of a variable. In C++, and actually it drew from earlier languages, functional languages, it'll figure out what the type is for you by looking at the operations on that variable. So cool. Take programming languages. I think programming languages should go into this if you study functional languages, but it's kind of a cool feature that's been introduced in C++. And I think has Java done this as well? Maybe not, I don't remember. Okay, so this is, so just follow along with the reading. I've tried to line these sections up with what we're talking about in class, so you'll have at least the kind of guidelines to how you'll generate assembly code. Yeah. Oh, yes, sorry, I have not uploaded yet, but I'll get that done as soon as I can. Feel free to remind me on EdSTEM if I forget. I have another sort of packed day with meetings today. So remind me if I don't get to it. So I try to get them up. It's something I do on my own. It's not kind of like not officially part of the UCF course. I sort of do it on my own. So I have to just do it. Yeah.
No, it doesn't like it. If you put auto and then any type, it says invalid combination of type specifiers.
Oh, okay. You can't even put auto. It still says it. Okay. So I don't know I don't know if it's a type name, because you can say auto int, right? You're allowed to say auto int.
You can say that in C.
Oh, so maybe C++ just changed the meaning of auto. So I think that's kind of true. It's true for static as well. Static is different. But anyway, this is C++ stuff. Okay, any other questions on the compiler project? This code generation handbook, which I'm sure everyone read last time. Questions on the homework? So again, talking about auto and say,
Yeah, I didn't, number 3, I didn't understand how to answer. It was like, what is created, what is caller created and column created, and I didn't understand that, because like, nothing's created, we just registered.
Okay.
Like, I understand the idea of callee set versus caller set.
I see.
That's what it was
I
asking.
may not have covered this thoroughly enough last time, but let me go over it. I may not have covered all of this. I may not have covered the callee save stuff. I think I wrote the homework before I did the lecture, so I may not have actually gotten to it. But let me go over it. Let me go over it now. So I think I did go over the callee versus caller stuff, but let's talk about the ones I'm pretty sure we did go over. So local okay. So first of all, for context here, to simulate. Remember we talked about last time local variables, how local variables get simulated at assembly time. You can't just allocate a memory location for your function variable, because if you have recursion or lots of nested calls, that data will be overwritten between function calls. And so you really want the variables to be specific to each call to the function, not each definition of it. And the way this is implemented in Intel, this application binary interface, is by using the stack to store function variables, function local variables. So on this page that I took this diagram from, if we have a function call here that has these 3 local variables, x, y, and z, the function will make space on the stack by effectively pushing space on the stack for these 3 local variables. And for parameters, their first 6 are going to be passed by the caller. So there are 8 parameters here, so the first 6 will be passed via registers, and the remaining 2 will be passed on the stack. So the green part here is what is caller saved. So this is what the caller does to create the stack. So this whole section here is the stack frame for the function. Yeah.
You said the green part, like that's the green part.
Yeah. Oh, sorry. Oh, yeah. So the stack allocated parameters. So basically, parameters and the return address are the caller, because the caller knows what its next instruction is. The callee doesn't know. The caller is just the next instruction pointer, and the callee saves the old base pointer and creates local variables. So everything from RBP on down is the callee, and RBP up is the caller, or excluding RBP, but above RBP, the new base pointer is the caller, that is the function doing the calling. Because the function doing the calling has the values of the parameters, and it has its own return address. And the callee, the function being called, will save the base pointer from the caller and allocate its own local variables. So that answers the old base pointer local variable. So that answers these. So the register parameters, I guess created. The registers aren't created, but the parameters are created in the registers. I guess that's, maybe weird wording. And then the callee saved registers, the callee saves these. So the callee saves these registers on the stack. I think I didn't cover this last time, but I'll go over it today or on Monday. But this diagram shows you which is caller and callee. So the caller, the function doing the calling, does the return address and the parameters, and the function being called does the old base pointer and the local variables. Does that answer your question? All right, other questions on homework? So function local variables, if we do auto, that is just when you don't have any other qualifier for the type, you just say int x within a function. They're allocated at runtime because they're only allocated when the function is called. And so this is kind of a variation of the same question. If you have a local variable x, will it only ever be in a single memory location at runtime? Not necessarily, because if you have recursion or multiple function calls, then every call will be allocated a memory space, potentially different memory space for that variable. We went over 3. And number 4, which register holds the currently executing stack frame? That's the base pointer, RBP. And the number, so the most number of active stack frames for factorial here. So we call factorial of 5. How many stack frames will there be for factorial? 5, maybe, I think that's right. Something around 5, plus or minus 1. Questions on that?
That's 8, because I counted all of them.
Yeah, if you count main, you counted main, right? Yeah, so if you just got the point that it's at least 1 per call to factorial, then that's right, yeah. There is a stack frame for each recursive call. So, but n is 5 here. So we have the first call to factorial, so that's 1. Then n is 4, n is 3, n is 2, and then when we call n of 2, when we call 2, it's 1, but n is less than 1, so we return. So that gives us 5 stack frames for factorial. So main is a function as well, so that'll be like a 6th stack frame. So I just wanted to remind you of the fact that each call gets its own stack frame. Other questions on the homework? So I've redesigned the notes a little bit on the functions. I realized I wasn't really getting to examples fast enough. It was like a lot of conceptual stuff. So I've reorganized the notes a little bit, and I'm going to do a lot of examples today to show you how these functions get implemented in assembly. So hopefully last time I convinced you that if you just do a kind of naive function call implementation where you just branch to the code and branch back and try to allocate space for each variable, it's not going to work. You know, the Fibonacci example, that's not going to work. So if true function local variables, you get a new instance of those variables every time you call the function, not for every definition of it. So that means it's not at compile time that you allocate space, but at runtime. The hard part about that is you need to generate assembly code. We'll talk about that more on Monday, but what makes this hard is that we're doing compilation, we're translating. So we need to generate code that's going to create memory at runtime. We're not actually going to be trying to create that memory or allocate that memory at compile time. That's what's going to make this hard. But I first want you to understand how functions are implemented in assembly. And so I've added a bunch of examples, a bunch of sort of small examples that we can build up to a more complicated example. Okay, other questions on the CodeGen project? Functions, homework? Okay, so okay, let me go back to where we left off. Okay, so what is a function? What's a definition of a function? Any takers?
Chunk of code that returns something.
Okay, a chunk of code to return something. Also takes inputs. So you can name it. It's abstracting away some computation, and you define its inputs and its outputs. That's really all a function is. But as we saw last time, if we want the semantics, the behavior of a function, like we have in C or other languages where it has its own function local state, we need to do a little more than just jumping to or branching to a sequence of code and branching back with some return value. Okay, so here's some simple IR code that illustrates a function call. There's no parameters, there's no local variables, it's just a call to this function f and a function that only returns at 5 every time. So not a super interesting function, but I will use this to illustrate what the assembly code version of this function looks like without any function local variables or anything like this. So questions on this code, the behavior of the simple IR code? Okay, let's see what this looks like in assembly. Oops. So in assembly, the way you define the target of the branch, the way you define where the function is in memory, is you can just use an assembly label. The assembler and the linker will turn this into an actual memory address, and the loader will turn this into a real memory address, but in the assembly language, we can just give a label to this. So has anyone not seen labels in assembly? If you did MIPS, I'm pretty sure you would have had labels for branching. And we saw this when we, this is also simple IR uses labels. So this is our function definition. It's just a label that you branch to. To call that function, there is an instruction whose mnemonic is call in the Intel world, but all call does is it just saves the return address and branches to f. That's all it does. So if you didn't do anything special for local variables, you would not have function local variables. You would get that wrong Fibonacci sequence behavior we saw last time. So that's all call f does. And there's also return, which unlike in C, it doesn't return any values at all. It just branches back to the return address. So all call does is it retrieves whatever that return address was that was saved by call, and then just branches back. Yeah?
Are call and return like actual single instructions that get run on the CPU, or are they like just like macros that get compiled into multiple instructions?
That's a good question. So are they actual instructions in the Intel? I think they are, but in the Intel architecture, from what I understand, underneath the hood, there's microcode, almost like code that it will implement these functions in terms of the actual physical hardware. So I think from the perspective of us, I think it is. I think it has its own opcode. I'm pretty sure, and we issue it in binary. But I don't think the assembler decomposes it into different instructions. I think it is. Anyone correct me if I'm wrong, but I'm pretty sure in the Intel world it is its own opcode from the ISA, the instruction set architecture point of view. But under the hood, it is just doing basically. You could simulate. You don't have to use it. You could save the return address yourself and then branch yourself using a jump. Yeah, we'll see more assembly, but you just call it jump. Okay, so that's all call and return are in the assembly level. So in order to do a return value, we have to save that value somewhere for the caller. So this is main. Main calls f, and then stores its return value somewhere. So RAX, by convention, holds the return value. So all F does is it saves or moves 5, immediate value 5, into the A register, RAX. And after, in the caller, the main, after the call returns, then it saves that return value, which is in the R register, into a variable. And I'll go over this later, what this actually means, but this is how you access variables, function local variables, in the assembly world. Okay, so questions on this? So let me illustrate what this looks like. So here's our code. I've added line numbers to represent memory locations. And so, each of these instructions will be in memory. And when you do call F, it'll branch to address 1. Yeah?
So when we want to return something from a function, we always put it in RAF.
That's right, yeah. Yeah, this return is not like the C return where it returns control to the caller and gives it a value. It just returns control to the caller. And in assembly, if we want to save a value for the caller to use, by convention, we use the A register to hold that value. So that's the calling convention that I started talking about last time. Now, you could use any register you want, actually. You don't have to use RAX, but the convention that's used by our system that we're compiling on uses RAX. So if you want to call other C functions or have C functions call you, your simple IR functions, use RAX for the return value. But strictly speaking, you could use any feature of the architecture you want. You could use the stack, you could use a memory location, you could use a different register. As long as the caller and the callee agree on how the value is passed, then you can use anything you like for it. Does that answer your question? Yeah, question?
So would it be accurate to say that the R, A, B, C, D, X registers or any other ones, like you were saying, are basically like static variables, and then any offset from your base pointer or like local variables?
Yeah, that's pretty accurate. So yeah, you could think of registers as like static variables. They persist across all function calls throughout your whole program. But static variables, but you have a limited number of registers. So if your program has like 100 static variables, you wouldn't be able to use registers for all of them. So the static versus dynamic is whether at load time there is memory allocated for the variable versus runtime on the stack. But to say that, yes, offset from the base pointer. What's that?
I'm just trying to analogize this to C++.
Yeah, so yeah, static is, well, so I think this diagram, this diagram that I showed last time kind of illustrates the difference between static and dynamic. So in statically allocated, so this is the executable file, this is what the assembler produces. So in your assembly file, you can allocate static global variables. So static means different things in different languages, but global variables are allocated at assemble time, basically, at compile time. And those values are just copied, or those locations are just placed into memory at load time. But there's no allocation in the assembly file for dynamic variables, for function local variables. Instead, at runtime, these values are pushed and popped from the stack. And we'll see what the code actually looks like to do that after we get through the basics of function calls. All right, so here is our assembly program that does a simple function call from main to F, or here I put start as an entry point. All right, so there's several pieces of information that the machine will hold for us. We have the instruction pointer. So the instruction pointer, also called the program counter on different architectures, this holds the address of the next instruction to execute. Questions on that? I think you should have learned this in MIPS, right? There's a program counter. It holds the address of the next instruction to execute. And we have something to hold the return address. And I'm going to hold off on saying how we do this, but we could use a register, we could use memory, but we need to hold that state somewhere. And RAX is used here, so let's put a space for RAX. So IP is a register, instruction pointer is a register, RAX is a register. If this is 64-bit, it's called RIP, which is sort of a joke in the security community because this is how you take control of somebody else's machine, by controlling this register. So we have the RIP register, the RAX register, and somewhere to store the return address. With me so far? Questions on this? So as I sort of mentioned, probably pretty quickly, when we talked about loading, going from the source code down to the loader, the operating system needs to know where you'd like to start in your program. So by convention, this is _start. The _start label is the entry point to your program. That's what we'll eventually call main. So in the Linux, Unix world, this is where the loader is expecting to find the first instruction. So upon loading, the RIP register will be set to whatever the start label is, which is instruction 3 here. Questions on that? So this is where we've loaded our program here. This is our program. We've loaded it, and this is the state of our machine. These values may have data in them, but they're going to be overwritten, so it doesn't matter. Okay. So when we issue the call instruction, what does call do? Call does two things. What is the two things that call does?
Save the return address.
Saves the return address and branches. So what's the return address? So the return address is the next instruction to execute in main. So what's the next instruction that's going to be executed after the call? 4, right? So when we issue the call operation, it first saves the return address, which is just the next instruction in that function. Because remember, what a function does is it pauses the caller function and then runs the callee. So main pauses until function completely executes, and then it continues executing after the function call. So that's the behavior of a C function. So it saves the return address here, and then branches. So what does a branch look like at the architecture level? Well, it's just changing the instruction pointer. So what's the instruction pointer? What does the instruction pointer get changed to when it call branches to the F function? Changes to 1, right? So call will save the return address, which is 4, and then just change the instruction pointer to be the address of the function to be called, the address of F, the callee. Questions on this? So if you took computer organization, I think they talked about the fetch, decode, execute cycle, and the way it works is it just fetches the next instruction, decodes it, updates the instruction pointer, and executes, right? Something like in some order. I'm not a computer architecture person, but at some point it's just going to increment the instruction pointer, and the only difference between execution without a branch and execution with a branch is that when you don't have a branch, you just add 1 to the instruction pointer. When you do have a branch, you just change it to whatever that label is, that address. Okay, so we've saved the return address and we've branched by going to instruction 1. Okay, so the first thing, when we execute move immediate 5 into RAX, that updates the RAX register to hold 5. And in the normal kind of fetch, decode, execute cycle, the next instruction pointer is 2. With me on this? So the machine will just sequentially go through each instruction until it sees a branch or a halt instruction. And now we're on the return opcode. So what does return do? The two steps that return does. Yeah, it retrieves the return address, setting it to RIP, and then that's it. It branches. So it gets the return address, which is 4, and then branches to 4. So it's going to update the instruction pointer to 4. And now we're executing this instruction, and this will move the return value into what I haven't kind of explained yet, but it will move it into the variable that the original program asked you to save it to. So the original program said save this into the retval variable. That's what this represents. This represents the return value, the retval variable. And I'll show what that looks like, but just for now, just pretend that this is just retval. And that's it. So that's the whole program. So you can hopefully see how this is equivalent to our simple IR, because we've made the function call, oh wait, that's not the simple error. We've made the function call and saved the result of the value into retval. And the way that worked was through using the call and return opcodes in assembly and using RAX as the return value. Questions on this? Okay. So let's see what it looks like when we've got multiple nested function calls. So if we just had one slot for the return address, that's not going to work, right? If we've got something like this in assembly where we have two nested calls, we call G. So remember, this is our entry point. We call G, and then inside of call G, the first thing we do is to call H, and that will branch here. So hopefully you can recognize that now we have two return addresses that we need to save. We need to save the return address that G needs to use, and we need to save the return address that H needs to use. Make sense? Questions on the behavior of this code? So this shows you why a stack is a good data structure for representing function calls. Because whenever we have a function call, that caller is waiting for the callee to return. So if we have another function call and another function call, well, there's always going to be a linear sequence of function calls, and the last call is going to end first, return to its caller, that's going to end, and that's going to end, and so on. And so a stack represents, because it's first in, last out, that's how we can represent this nested sequence of calls. Okay, so let me show you the same state. So we have the instruction pointer. We've got RAX. So I only have a single return value here. But the return value is going to be sort of less important for this example. And then I have the stack. And I'm going to, by convention, draw the stack upside down from what you're used to, because this is how it's represented in memory. So we start at the high address. So our stack starts here and grows downwards in memory. Okay, so what's our first instruction pointer set by the loader? 5, because that's, by convention, the start address. And then the first thing that happens is we call function G. So what does the call do? It first saves the return address. Return address is 6. So here, when we save the return address, we push that return address onto the stack. So instead of having this where I didn't tell you what, in the architecture we use, it could have been a register, it could have been a memory location. Here, we push that return address onto the stack. And then we branch. We branch by just going to the next instruction pointer. Then we branch to whatever the instruction pointer for G is. G's memory location is 3, so the instruction pointer is updated to 3. And we continue executing. Questions on this? First thing we do is a function call. So what does a function call do? Saves the return address. And we do that, and so the return address here is instruction 4, right? It's the next instruction after the call. And we push onto the stack that return address. So remember, we're going downwards, so this is our first function call. This is the function call for call H. And then we branch to H. H has instruction pointer 1. Yeah?
I thought you needed to use push to push the return address.
Yeah.
The stack return address.
Yeah.
Is that like happening with call?
Yes. So, actually, I didn't make that clear. So call will push. Call actually does a push onto the stack.
So when you put the return address onto this, is that its own stack of return addresses, or is that part of the stack?
So for this program, call will just push onto the stack. If we want other stuff on the stack, we have to write assembly code that will put it onto the stack.
So RVP minus however big the return address is always going to be the return address.
Yes, exactly. Yeah. So we saw that. We'll get there. We'll get there. But yes, that's right. But at the, in terms of what these operations do, so this is why you as the compiler writer have to generate additional code that will manage local variables on the stack. The Intel architecture is not going to do that for you. What it will do is it'll push the return value on the stack for you, but that's it. It's not going to update the base pointer. It's not going to allocate space for local variables. It's going to do nothing to the base pointer. All it's going to do is push the return address onto the stack and then branch by changing the instruction pointer. That's it. That's all you get with call. Okay, so we've just called H, and remember that pushed the return address, which was 4. That's after the call to H. And now our instruction pointer is 1. It does a move immediate of the value 7 into RAX. Then because of the fetch, decode, execute cycle, the next instruction pointer is 2, and it's a return. So return does the opposite of call. It first pops the return address off the stack. So when you call, so we're on return here, we're on instruction address 2. The first thing it does is it pops this value off the stack. So it pops it off the stack and then branches. So we popped 4 off the stack and branched by setting the instruction pointer to be 4. That's all return does. Questions on that? And so that gives you this return behavior, because now the next instruction is where we left off in G. And so G calls return as well. So what does it do? It pops the return value off the stack and branches, putting us back into the main function. Now from the assembly point of view, this is all just a straight line sequence of code with branches. So in some sense, there's no difference between functions and not functions. In assembly, it's all just straight line code. All the functions just get laid out in memory as just a block of code. But it has branches between it. So it's kind of just a kind of special form of branching function calls, where we save what the last or what the next instruction was going to be after the branch. Okay, and then our last instruction is this move RAX. This is just saving the return value into a variable. Questions on this? Questions on this behavior? Is that more clear? Hopefully, I think hopefully it's somewhat clear. So that's all you get with assembly or Intel call and return. It's just a fancy branch where it saves the return value for you and restores the return value. And yes, it uses the stack to do it. It calls. It does the same thing. You could avoid using a call and just say push and branch, push and jump in the Intel world. Okay, so let's see how, so we went over function local variables. So let's see how, we went over this already. So let's see how local variables, how we can handle local variables using the stack. So here's an example of a simple IR function. It's called example variables, and it defines 3 local variables, a, x, and y, and it assigns x and y to something. So it assigns x to 1, and then assigns y to whatever x is, which is 1, and returns 0. Questions on local variable, or questions on this simple IR program? Okay. So the Intel architecture gives you some functionality to use memory as a stack. So there's a special register called the RSP register, stack pointer. So SP means stack pointer, R means 64-bit. And it always points to the top of the stack. There's an op for push, which takes some register or memory location or immediate value, puts it on top of the stack. Pop will take a register, I think only a register, and it'll pop that value off the stack. And the way these are implemented is that, so as I illustrated here, the stack starts at a high memory address, and then when you push values onto the stack, the addresses get lower. You subtract values from the address. So the implementation of push and pop, you could also do without push and pop. You could do with just move and add and subtract instructions. So push just subtracts an address from the stack pointer. So the stack pointer is pointing here, and when I call push, it just updates the stack pointer to point to the next memory address, and moves that value into the memory address. When I call pop, it adds to the stack pointer. So that's all push and pop does. It just adds to the subtracts from the stack pointer, copies the data into memory. Pop will copy data from memory and then add to the stack pointer. So by doing that, the stack pointer will always point to the top element on the stack. Okay, and so here's how you could implement push and pop yourself. So calling push RAX is equivalent to subtracting 8 bytes, because we're in the 64-bit world here, subtracting 8 bytes from the stack pointer, and then moving RAX into the memory location that's pointed to by stack pointer. And again, I'll go over more about these addressing modes in Intel, but I just want to show you kind of how you can implement yourself push and pop. So pop does the opposite. It saves that value back into RAX and then adds 8 to the stack pointer. So remember, we're subtracting 8 because the stack by convention grows down in memory addresses. And so when you pop, you add 8 to the stack pointer. Questions on this? And I'll go over the different kind of syntax here for the addressing modes in a second. Okay. So remember last time what we talked about is how we can have function local variables is whenever we have a function call, we make space on the stack. We make space in memory. We'll use the stack for this because when you have nested function calls, a stack is a good data structure for storing that because it's first in, last out. So in this example, we didn't have any variables. We just call and return. We'll push and pop the return address from the stack. But we can also use that stack for function local variables. So here's our example where we have some local variable allocation. And I took out all the assignments because we'll get to that in a second. So here is how we can write assembly code to allocate space for us on the stack. So you could use a push or you could use a subtract. Here I've used a subtract because subtracting 8 from the stack pointer is the same thing as pushing to the stack pointer. So doing this will mean there's no initial value to your variables, right? Because you just subtracted space. But here's how we're going to start and end our function. As soon as we get into our function, as soon as we've branched to our called function, we're immediately going to subtract from the stack pointer. We're going to push 2 slots on the stack pointer, push 8 and push 8. Push 8 bytes, 8 bytes. And now we're going to have 2 slots on our stack pointer. So here's what this looks like on the stack. So here's our stack. The first thing that's going to happen is when someone calls. So I didn't show the call here, but when example variables gets called, the return address is going to be pushed onto the stack, right? Because that's the call. So this is what the caller did. And now our first instruction in this example variables function, what's the first thing it does? Okay, so let me also show the stack pointer here. So the stack pointer is pointing to the top element on the stack. So after the function call, after the call instruction, the top of the stack holds the return address. That's what it'll hold as soon as we branch into our function. Questions on that? Does that make sense? So that was the example I just showed, where the call will push the return address onto the stack and then branch to the example variables function. So now we're on this instruction. We're on the first instruction of the example variables function. So what's the first thing it does? It subtracts 16 from the stack. It makes 2 spots on the stack for our local variables. And so it does that by just subtracting 8 twice, subtracting 16 from the stack pointer. So you could also do 2 pushes. So if I pushed once, this would be the top of my stack. I push again, and now this is the top of my stack. So this is also why in many C compilers, if you initialize a variable, you declare a variable, but you don't assign it to anything and try to print out the values, you may get garbage data. But what that data is really just whatever values are in the stack when the function was called. Questions on this? Questions on this? Now, if we were to return immediately here, what would happen? If we just called return now, we didn't have this line, we just called return next. What would happen with the return? What does the return instruction do in Intel? Yeah, go ahead. Yeah, it pops. It pops whatever value's on the stack and branches to it. So if we forgot to pop this stuff off the stack before we called return, we're not going to be returning to this return address anymore. We're going to be returning to whatever data was in here. And if we haven't done any initialization, or say we initialized to 0, what's going to happen when we try to return if the data is 0? You've probably seen it. You're going to get a seg fault because you're trying to work with data memory that you don't have access to, that the system has access to. Or you might have garbage data, uninitialized, unknown data in here, and you may actually branch to a part of your program that you didn't expect to branch to. And the machine will just start trying to execute code. You'll probably get something like unknown opcode or something like that. You'll get some error. But if you have a really clever attacker who managed to fill this data with, say, shellcode, code that will run, bash shell, especially if your program's running as root, then this is like the classic stack smashing attack, where attackers will take over your program by branching to code that they have inserted into the stack. Okay, so we've branched to our example variables function. We've allocated space on the stack for it. And that's how we get our function local variables. And that's how we get it every time this function's called. Because every time this function is called, even if we have recursion, so if this was recalled again, for instance, if somewhere in here example variables was called recursively, then what would happen? Well, we'd push a new return address and then allocate 2 more spots for the new call to example variables. So it would have its own function local variables. But okay, so I'm getting ahead of myself a little bit. But here's what the state of the machine will be when we start executing the body of this function. Once we're done, we're going to end the function by restoring the stack to what it was before we had the function call. So we're going to just remove 2 elements from the stack. So you could do pop twice. Here I've done add 16, because remember the stack goes downwards. So when I add 16, my stack pointer is now here. So now what happens when I call return? Yeah, it pops the return address. And this is the expected behavior of the function call, is that it pops the return address that the caller actually set. All right, questions on this? Yeah.
Not exactly related to this, but just to clarify, the RBP would point to the entire stack frame itself, right? Not like the RSP that points to what we know on the stack.
You're actually leading to the next part of the slide. So yes, RBP is how we're going to sort of remember where in memory these variables are. Yeah, I'll get to that next. Yeah, I'll get to the stack base pointer next. Any other questions on this? Yeah.
Random about simple IR. Did it support arrays or?
No, there's no array construct, but it does support pointer operations.
Okay.
So you can, hopefully you learn this, that array accesses are just pointer operations.
So is there any way to reserve a certain amount of space to an array?
Actually, no, there's no dynamic allocation.
Not dynamic allocation. It's saying create an array with say that.
You could just have a bunch of local variables, like A1, A2, A3. That's how you can simulate compile time sized arrays, fixed array sizes. But you can call malloc from simple IR.
Yeah.
So you can have dynamic variable size arrays if you want. Okay, other questions on this idea? Yeah.
So you were talking about kind of we leave a variable undeclared, we don't
Yeah.
and there's garbage wrappers there in the stack. How does the garbage get there though? Because the stack is allocated by the operator.
Oh, that's a good question. Like, why would there be values in here at all anyway? Like, let's say the OS initialized everything to 0. If you had a function with a series of function calls, you call it, like if you have main and it says calls F, then you call G, then you call H. Whatever data F had, G will now potentially see on the stack. Because all I've done is I've just changed the stack pointer. I haven't actually cleared any of this data. That data is still in memory. So if I call example variables again, let's say I called example variables and I put 9 and 10 in here, and then I call a different function, and that function allocates, let's say it allocates like 3 spots. These values are still going to be in memory. Even though the other function will, let's say the variable z was allocated to here in the second function call, then z will have value 9 if you try to access it. Does that make sense? So it's because whenever you make a new function, you push it onto the stack and then pop it when you're done. So if you then make another function call, it's going to allocate space on the stack. And if you're not clearing memory, if you're not setting memory to something, it's going to retain that value over multiple function calls. But yeah, good question. Okay, so let's get into RBP, the base pointer, what the RBP looks like. So what we're going to do is so in our language, to make things simple, everything is a 64-bit integer, 8 bytes. Having multiple data types is really more of a bookkeeping thing if you want to allocate arrays or structs or different sized data. You just keep track of all their sizes. But to make things simple, everything in simple IR is 64-bit integer or 64-bit, just needs a 64-bit slot of memory. That's 8 bytes on the stack. So everything in our language is going to be an 8-byte address. And so we're going to assign variables. So when we allocate space on the stack, we're going to assign variables to each of these memory locations. So that's going to be the strategy we use. And so in order to keep track of where these variables are, we're going to use a special register to hold on to the location in memory of these local variables. So what we're going to do is, as soon as we allocate space onto the stack, we're also going to save the first variable. We're going to save the location of the stack frame. You could call it the stack frame itself, but it's really just pointing to the first location. So there's going to be other stuff in the stack, but for right now, let's just say the RBP points to the first variable that gets allocated. So the stack pointer is going to be here at the top of the stack. But before we do that, we're going to save the location in memory that of the stack frame itself. That is the first address in memory when we made the function call. So you might be asking, well, why not just use the stack pointer? So we know the stack pointer. We know if we allocated 2 slots here, we know, and this is X and this is Y. Well, Y is at RSP, and X is at RSP plus 8, right? This is the RSP register. This is RSP plus 8 in memory. So why might we want to have a separate register instead of the stack pointer to record where X and Y are in memory? So why bother having 2 pointers here? So we have 1 pointer that points into the stack, and then we have the stack pointer which always points to the top of the stack.
You can add another one.
Yeah, you mean with push. But you add another. Well, so yeah, so the stack pointer and push and pop, they're general purpose instructions. So your program might have push and pop in it. And so if your program starts calling push and pop, it may have memory, it'll be hard to figure out where X and Y are in relation to RSP. So it's not going to be RSP plus 8 anymore if you call push and pop again in the course of your function. So the way we get around this is we have a special register RBP that will always have, it will never change throughout the call to the function. It'll always point to, in this case, the first variable that we allocated. So stack pointer can go wherever it goes whenever people call push and pop. and the base pointer will always remain here. Anyway, that's a minor thing. Just remember that the base pointer doesn't change throughout the execution of the function, and it always points to basically the first variable. Basically points to that list of variables that you've allocated on the stack. Questions on that? Yeah.
So if we don't have more than 6 variables passed to your function, does our BP not matter at all? Because you just have register saved variables?
Well, so that's for parameters, but you could have local variables. So for instance, you could have no local variables no parameters and all local variables, and then you would need space for those local variables.
Every single local variable gets space.
Yeah, every local variable, without optimization, every single local variable, you can think of having a space on the stack for it. Okay, and the way we're going to access these, the way we're going to keep track of this in the compiler is that, in the assembly world, we don't have names for these. This variable, there's no way to name the dynamically allocated variables, so instead, we're just going to keep track of offsets from RBP. So I have this, so there's one piece here that I haven't gotten to, which is why these addresses are a little wrong. They look like they're off by 1 slot. But so if this is RBP, one way we can allocate space for each variable is by assigning each variable to an offset from RBP. So if we made this slot for A, we allocated this slot for X, this slot for Y, then if we want to access these in the assembly file, we know we can always start with RBP. RBP is not going to change. So we can always just add to RBP in order to find which variable we want in memory. Yeah?
Do we subtract the offset since it goes down?
Oh, sorry. Sorry, I said minus here. Yeah, it's subtract. Sorry about that. Yes, it's subtract. This table is right. So we subtract from RBP. So the reason I was adding this A is because we also need to allocate space for the callee saved registers, but I didn't want to show that yet. But unfortunately, I made this probably more confusing than it had to be. But no matter where our compiler allocates these variables, if we make them a fixed offset from RBP, we can always access them during the execution of the function. Does this sort of make sense, this diagram? So if we save RBP here, regardless of where our stack pointer is, our stack pointer might be somewhere down here. Even if the stack pointer changes, RBP doesn't change, and we can always access these stack allocated variables by fixed offsets from RBP. Yeah. RBP is a pointer. So these are, okay, so that's also what's a little unspoken here. These are memory addresses. So if this is my hex math is going to be bad. My hex math is bad. So let's say this was address 128. This is going to be address 120 because these are 8 bytes each. So it's going to be address 116. It's address 108, 100, etc. So RBP just holds 120. So the RBP register will hold. So this is like pointers. This is pointers in C. So what does the pointer value hold? It holds a memory address. That memory address is just a number, and that number corresponds as to how you can access values in RAM or in memory. Does that answer your question? So it's literally the memory address of this place in memory where the stack has written in memory. All right, other questions on this? So this is the key trick to having function local variables. We save a pointer, RBP, to the stack before we start allocating variables, and we never change that pointer. We keep that the same throughout the whole function call, and we allocate space one time at the beginning of the function for all of our function local variables. And then we know that there's always a fixed offset from RBP for each of those variables. So when we generate code, our generated code doesn't need to know about what the actual address is going to be at runtime. All we need to know is these fixed offsets from RBP, fixed offsets from this pointer. And so when we generate code to read and write these variables, We just change them into code that reads and writes from address RBP minus some offset. Yeah. Yeah.
Just a quick question.
Yeah.
What is the A storing? Because I know we have.
Oh yeah, so I just forgot to put A. I forgot to put A here. I probably just leave this as XY. It's just when you see the actual code generation, you have to save some additional. You have to do some additional stuff to the stack to save. You have to save the RBX register basically, and there's other stuff you have to save on the stack. So I probably should have just like left that for later instead of doing that here. I don't know if that makes sense, but if A is here, then these are going to be your offsets. Yeah.
And the offset is just something that the developers know, right? Like we're aware that if there's 3 variables and if we want to access like say Y, we just subtract 1.
Yeah.
We store that offset in some way.
Yeah, in your compiler, you will actually have a table that stores this during compilation. So your compiler will create a table that produces these offsets, and then it'll use that whenever we. That'll use that whenever we see A or X in our program. We'll translate that to a memory load or store that uses this offset from RBP. And I'll show that as well. So we'll get there as well. Yeah.
Wait, so what's that address 120?
So there's. I shouldn't have foreshadowed this, but basically there's going to be a pointer to the old stack frame.
Okay, so
Yeah.
Wait, I was just making sure it's not just like empty.
No, it's not going to be empty. I was trying to find a way to build up to all the pieces, but I think I got it a little wrong here. I probably should have just made this like offset 0. But then I'd have to tell you later that there's going to be other stuff there on the stack. So it's kind of just a pedagogy problem where I had to order things that I show you. Okay, but let's get to those other things that are stored onto the stack. So here's how you, but first let me show you how you access, in the assembly world, here's how you can access stuff from register pointers. So if you have a pointer, you have a memory address and a register, the Intel world at least gives you some variations of the move instruction that will let you make it convenient to access memory like this. Okay, so let me go walk you through some of the move instructions that you have, the addressing mode and move instructions in the assembly world. So this is how you move a constant value in the assembly world. So this is called the AT&T syntax, which is what GCC uses. The destination register is on the right always. It's the second operand. So this will store the integer value, the literal value, binary 1, into this register. Questions on that? So we're just changing the register's value to be this binary 1. So this doesn't do any kind of memory accesses. This is just changing the register. Similarly, you can move between registers. You can copy data between registers. This copies the data in RAX to RBP. Now this will actually overwrite RBP. So if you had a pointer here, you wouldn't want to do this. You don't want to overwrite RBP. What we really want to do is we want to treat RBP as a pointer and dereference it. We want to access the variables in memory that are at the address held by RBP. Yeah?
On a compiler where you support multiple data types of different sizes, will the main challenge be the offsetting?
Exactly, yeah. That's exactly it. Yeah, so you just keep track of what the offsets are. That's exactly right. Yeah. So you can think of those data types as just memory sizes in a compiled language. Okay, so this is how we do pointer dereference in the assembly world. If you put parentheses around a register, this is not going to overwrite RBP. This is going to do a lookup to the address stored in RBP and store whatever RAX is. So let's say RAX is 1. This is going to store, so this would store 1 in the memory address held in RBP. So this is like doing star in C. Questions on this? This is just the syntax for it in the assembly world. And there's one more addressing mode that the Intel world gives you. If you put a number before the parentheses, this is an offset. So this will take whatever the address is of RBP, and it will subtract 16 from it. So that'll give us this address, and then it'll do a load or store at that memory address. So this is kind of like an array access. So this is like saying, RBP, if RBP were an array, putting like the index brackets and putting 16 in there, if this were a byte array. Or putting -16 rather. That kind of makes sense? So this will look up the address, take the value in RBP, subtract 16 from it, and then do a load or store at that address, given by RBP minus 16. And so this is exactly what we want if we want to be able to access this memory location here. So if we want to be able to access variable X or variable Y, if we use this addressing mode, we'll access the memory associated with that variable. So what that means is if we have an instruction like this in simple IR, how do we translate that into assembly code? Well, there's a couple ways to do it, but here I'm first setting 1 to RAX, so now RAX holds the constant value 1. And then I'm moving RAX into this memory location. So I'm moving whatever the value of RAX is into this memory location that's associated with X. So you can think of the compiler as just taking variable names and translating them to these indirect memory accesses. Yeah.
So those memories, like those memory locations, would have created and it's like utilized each other.
Yeah. Yeah. I think so, yeah. I think if I'm understanding what we're saying, yeah, that's right. Okay, questions on this? So once we've allocated space and memory, and we've saved a pointer to that stack frame allocation, memory accesses become basically array accesses. So if RBP is an array, arrays are pointers, we can use this Intel addressing mode to translate accesses of X, which the Intel world would have, the machine would have no understanding or no way to process a string value, and translate it into offsets in our stack frame, offsets into this sequence of allocated variables in the stack. Okay, so what would something like this look like if we're trying to take the value of X and assign it to the value of Y? Well, what does this look like on the stack? We want to take whatever the value of X is. We want to take this memory location and copy it to this memory location. This memory location is associated with Y. This memory location is associated with X. So we want to take whatever value is in here, let's say it's 1, and we want to copy it into this memory location. Now, in the Intel world, you can only do one memory operation per instruction. So we need to do this in 2 steps. So first, we take the value of X, which you can get using this memory indirect offset, this register indirect addressing, this pointer, and store it into RAX. So after this instruction is called, RAX holds the value 1, because that's what we assigned X to originally. And then we can store RAX's value into the memory location associated with Y. So this will store RAX into the memory address associated with Y, which we get by taking RBP, subtracting 24, and then storing RAX into that memory location. And so this is altogether what this assignment looks like. It's taking X, storing it into a register, and then taking that register and storing its value into Y. Questions? Oh yeah, questions? Yeah. Yeah. No, you could also do this by just moving 1. I did this because it's for me it's slightly easier to write the compiler, because you can sort of, So you could just do move 1 in. You could do a move immediate into memory as well. I just did this so that it would look very close to this assign instruction as well. That's why I wrote it like that. Okay, questions? Questions on this? Yeah.
What would happen if you mess up the offset and you don't go by 8?
Yeah, you get the wrong data. So you have byte addressing in the Intel world. So you can access individual bytes, I think, at whatever offset you want. So if you got it wrong, I mean, if in one instruction you stored X at -16 and another instruction you loaded it from -17, what's going to happen, right? You're going to get not X, not the thing you stored originally. And so, but this is the beauty of having RBP, is that we can, in the compiler, we can associate each variable with a single offset and save that for the entire execution of the compiler. So when we're running this, we're compiling our program, we fix these offsets one time. And so that way, whenever we have a variable usage, we just look up in our symbol table what its offset is. That way we're always using the same offset every time we see the variable usage. Okay, so let me show what I now think I should have shown first, which is what happens when you have multiple function calls. So just like the return address, we needed to save that onto the stack. What's going to happen to our base pointer? Well, yeah, so the reason I did this first is because the base pointer doesn't really make sense until you have variables, but then storing the base pointer doesn't make sense until you have multiple function calls. But let's say we have these two functions. So we've got function main, which has its own variable x, and we have function f, which has its own variable x. So if main is our entry point, and we call main, then there's going to be some return address from whoever called main. And what is main going to do? Main is going to have its local variables on the stack. So that's forgetting about the base pointer here. So it's going to have its own local variables. And so this is going to be main's stack frame. When main calls f, what's going to happen? We're going to get a return address into main. And then f is going to store space for its stack allocated variables. So this is f's stack frame. This is main's stack frame. The problem is if I have set RBP in main's stack frame and then I call f, I'm going to blow away RBP and set it here. So what's going to happen when I go to return to main? Well, now main's x is no longer an offset from RBP. RBP is still pointing here into f, but f is not running anymore. So if ret val is -0 from RBP, x is -8. Here, x is -8 here. If I'm back in main and I go to access this value variable x, what's going to happen? I'm at RBP here. If I do RBP -8, I'm going to get whatever this value is. I'm not going to get this value. So I need some way, just like the return address needs to be saved, just like the variables need to be saved, I also need to save this base pointer, because there's only one for the lifetime of the program, but I have multiple functions. So the way we solve this is when we create our stack frame for, so it's 1020. So basically the way we solve this is we're going to push onto our stack. We're also going to push the old base pointer. So when we get into F, we're going to push the old base pointer onto the stack and then push our variables. So that way when we pop, we can restore this old base pointer back to main's base pointer. All right, so I'll go over this next time as well. We have one more lecture on functions. And all right, everyone, have a good day.